Hello viewers, what's going on? It's again sciencing around. Happy sciencing to all. And here now I'm going to explain the part of physics which name is work, power, energy. Oh yes my friends, work, power, energy. And I hope this video would be quite small because in this time this is quite a vast topic, and now I'm going to explain a small part of it because I don't want to bore you by long videos. So just I would say about work, power, energy, and equilibrium. So let's get on with our first thing. So friends, first of all, what's work? I'm sorry if you feel this paper is spoiled because I created these notes almost a week ago, so I hope this would be spoiled because I read it everywhere I go. So let's come to the topic. What's work? As you can see, the whole motherfucking formula work equals to Fs cos theta, or we can say another thing, work equals to F bar dot S bar. At the last time in the video of vectors I told you what is dot product. So dot product of the force and displacement will give us work. So what's work? What would be its practical performance of work? Suppose it's an object of mass m. Mass doesn't matter. I'm applying a force F to it. I'm applying the force of 1 Newton to it, and the object is displayed at the displacement of 1 meter. I'm applying the force of 1 Newton, displacement is 1 meter, then work equals 1 joules. And now one more thing, I'm glad to say that this topic has very less and easily rememberable formulas, and it has a really high weightage in any competitive exams I've ever seen. So you'll be lucky enough to listen or to learn this chapter, as it's quite conceptual thing. So let me tell you, another formula of work is summation of Fn into delta xn, where x is the displacement, or the integral of fx dx. I hope you know the formulas of integration. If not, I'll make another video on that. So what is this formula says? If there are many forces, like on an object, the force is F1 is the force, F2 is another force, F3 is another force, and there are many displacements like x1, x2 and anything, then work can be said as F1 x1 plus F2 x2 plus all that Fn xn. This is the explanation of this type of fucking formulas. And work done from A to B, where A is the initial displacement and B is the final displacement, is fx dx. And another interesting thing, area under function displacement graph, that is, if I draw a graph where x-axis depicts the displacement and y-axis depicts the force, that is force versus displacement graph. Let there be any fucking graph between the force and displacement. Let this be A, let this be B. Then the area covered by this region is the work done by displacing the body from A to B. So guys, I hope this much is enough for work. Let's get on to another topic, which is power. I'm not taking here in this power, I'm not talking about electric power, which is I square R or V square by R, but mechanical power. What is mechanical power? Rate of work done per unit time, that is dW upon dt. That is work done per unit time. So power is work done per unit time. If you know about limits, then limit delta t approaching to 0, dW upon dt, dW upon dt, any fucking thing. And now another thing, we know what is dW as work equals to Fs, dW equals to F ds. So just substitute in here F ds upon dt, F ds upon dt, dW upon dt. What the hell is ds upon dt? Come on, I hope you know. ds is displacement upon time. Displacement upon time is of course velocity, so for F bar equals to power equals to F bar dot V bar. Very important formula, guys, for power. Power equals force vector dot velocity vector. So this was the most important things or concepts in the power. I will also solve problems on it, but right now let's come on to our next topic, which is energy. As you can see written in the paper, what is energy? Mechanical energy, the first form of energy which you have to study in mechanics. There are many energy like gravitational energy that comes in potential energy. Actually, mechanical energy is the main form of these mechanics. So mechanical energy divided in two parts, this kinetic energy and potential energy. Kinetic energy's definition always same, half mv square. This potential energy, actually this is gravitational potential energy. Actually potential energy equals to minus of work. This is the real formula for any potential energy. Learn it, do anything. It is the negative of work. Potential energy is the negative of work. And of course, I hope you know about the spring. If you don't, then every spring has a spring constant named K. We call it the force constant. So more decay, more would be the elongation. So this restoring force of spring, if it is elongated, then its restoring force would be kx. And I'm sorry, I think I wrote it right. It's not half mv squared. The spring energy is half of kx squared. The spring energy, the energy stored inside a spring, would be half kx squared. I hope you know about the spring, of course. So the spring energy would be the half kx squared instead of half mv squared. Remember the formula. I hope it's easy, related to half mv squared. I hope it's time to go to the next page. So conservative forces. So let's see what it says. Alright, so let me explain you the conservative and non-conservative forces by the examples. So the first example of conservative force is gravitational force. How the hell? You think in your mind, how the hell? So let this be any motherfucking block resting on an inclined plane. The block is at rest. And now listen to me carefully, guys. The block is at rest. The block is doing nothing, nothing, nothing and nothing. It's just a rest, silly block. Then too, a gravitational force is acting on it. G. Block is doing nothing. No moving, no movement, no upping, no motion, nothing. Then too, a gravitational force is acting, that is mg. Let this be m. So the gravitational force would be mg. That's why it is a conservative force. Now, simple thing. Let's take the simple block again for explaining the non-conservative forces. Now you tell me, guys. You answer me. If this block is at rest, then will friction force act on it? Will it? Absolutely no. The frictional force won't act on the block. But if the block is in motion, let the block be in acceleration, then according to the force, the friction would act backwards. That means the friction would only act on the block if the block is in motion. These type of forces are non-conservative forces. Simple is like viscous force. If in a fluid, if something is at rest, we are holding it, then viscous force won't act. But if it's going down, then viscous force would act. That's the funda of conservative or non-conservative forces. Now, next thing, when you use potential energy rather than by conservative force, dW is equals to minus of du. What I told in the back page, work is negative of potential energy. Our potential energy is negative of work. Therefore, Fx is du upon dx. Because by transport, take dx here. F dx equals minus of du. That means dw equals minus of du. That is this. Work is negative of potential energy by the simple city definition. Now our next topic, or I must say next subtopic, named as equilibrium. Very easy, guys, don't panic. This is very easy topic having a very good weightage. Equilibrium is obtained when change in potential energy plus change divided by change in displacement, means change in potential energy per change in displacement equals 0. What is du by dx? Minus of f equals 0. That means summation of each and every force equals 0. So basically there are three types of equilibrium. First is stable equilibrium. Now let me give you an example. Yeah, here is an example. Suppose this is a type of surface, V-shaped surface. Inside is a ball. Alright, I'm applying some force on the ball, or I must say some impulse on the ball. The ball goes. At some distance it must stop because of gravitational energy acting on it, and again it would come down and it would restore its position. So the equilibrium, that is, it again comes up and again settles down here. That means the equilibrium where the project or where the object is restored to its original position is stable equilibrium. And as opposite, and as you can see in the diagram now, if I make the ball fall from here, would it go up? Would it go up? No, it won't. So if its displacement is not 0 or if its final position is not equal to the initial position, then it's unstable equilibrium. And yeah, in stable equilibrium, potential energy is minimum. In unstable equilibrium, potential energy is maximum. Neutral equilibrium, d square u upon dr square, that is the double derivative of potential energy per displacement, equals 0. And in neutral, potential energy is constant. What is neutral equilibrium? A straight, simple plane. The ball is just we have to just apply a force on the ball. The ball is going straight away and settling at some other point. That is the neutral equilibrium, I must say. Now you must have a question: what is difference between neutral and unstable equilibrium? Main difference between them is potential energy. Here potential energy is maximum, that is going from an upper height to a lower height, and here potential energy is constant as the height is constant. Alright guys, so I hope you learned everything. I hope you learned something from this video. I hope, should we recap? Okay, let us. Work power energy. Work is equals to F bar dot S bar equals to Fs cos theta. Summation of work Fn dx. If many forces, many distances, then F1 x1 plus x2 s2 plus blah 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 blah. Power. Weight of change of work. Limits t approaching to 0, dB upon dt. Or force into velocity. Energy, mechanical energy, kinetic and potential. Spring restoring force, kx. Spring energy, half kx squared. Sorry about this fucking thing. And our next thing, that is conservative forces like gravitational forces. Even if this is motion, then gravitational force acts on it. But here, if it is motion, then frictional force never acts on it. And if it is in motion, then frictional force acts on it. I'm sorry, if it is in rest, then frictional force would never act on it. And if it's in motion, then frictional force acts. And when kinetic energy, then equilibriums. Stable equilibrium, restoring its position. Unstable equilibrium, never restoring its position, changing its height. Neutral, you see it. So guys, thank you for watching. Next time I will cover conservations of mechanical energies, and I will solve some problems on this session and even the next session. So I hope I'll upload it I'll upload it at my best and at very early time. And if you want any changes, if you want anything, if you want any changes in my video, and if you like my video, then please like my video. Please press that like button and subscribe my channel. I hope it won't take much time. And please comment in the comment box whether you like my video or didn't like, and what changes should I do, how should I teach you so that you could understand it better. Thanks guys, see you later, happy sciencing.